everyone, Miss Lorette here. In this video I'm going to be walking you guys through section 6.2. I'll be breaking this up into a couple of lessons. This is going to be how to solve linear systems using what's known as the substitution method. So you'll need something to write with, something to write on, and possibly a calculator. Now before we dive into today's lesson, let's actually take a look at a little logic puzzle. So I encourage you to pause the video here and see if you can figure out what is the value of cheese. You may have actually done logic puzzles like this in the past. This one's pretty easy, so give it a go. Okay, so hopefully you've given that a try and you've come up with some sort of an answer. Now when I look at the equation that has the cheese, in order to solve for this value, in order to solve for this variable, I need to also know what the cat is equal to. Well, I can't solve for both of these variables within this equation. That's too many unknowns. But if I look at the second equation, I only have one unknown, so I can solve for what the cat is equal to here. So I'm taking this value and adding it to itself 4 times. So I'm trying to think what number, when I add it to itself 4 times, gives me 50. Well, this is kind of like 4 times the value of 1 cat, because this is my variable. When we repeat addition, that's the same thing as multiplication. So if I do a cat added to itself 4 times, that's the same thing as 4 times 1 cat, which equals 50. So I can use an inverse operation. Inverse of multiplying is to divide, and I'm going to divide by how many cats I have. Each of them has to be equal to the same thing. So when I do that, I get a decimal. I get 12.5. So that tells me if I do 12.5 times 4, or in other words, 12.5 added to itself 4 times, I should get 50. So the value of the cat is equal to 12.5. Well, now that I know this, I can substitute that number for all of the cats in the first equation, and I can use that information to help me solve for the value of the cheese. Well, I'm adding 12.5 to itself 4 times in this top equation also. So if I simplify that, that's going to give me 50. So now I need to think, what do I add to 50 so that I still get an answer of 50? Well, the only number that's going to work here is 0. So hopefully we ended up matching. You should have gotten that the value of the cheese here is equal to 0. This is a very basic example of what it is we're doing today. We had 2 different variables. We solved for one of them, then substituted that solution into the other equation to help us solve for the other. So solving systems by substitution, here are the basic steps. The first thing that we want to do, and we might not always need to do step 1, so this is if necessary, but the first thing we want to do is isolate one of our variables in one of the equations. Either get an x by itself or a y by itself. So one of those variables is going to be equal to some sort of algebraic expression that uses the other variable. So think about equations in slope-intercept form. Y equals 2x plus 3. That y is by itself in that slope-intercept equation, and it's written as an expression that contains an x. Then what we're going to do is take that expression, the algebraic expression, from step 1, and we're going to substitute it into the other equation. This is really important. We're substituting it into the other equation, not the same one. At this point, we should have one equation with only one variable. Either it's going to be y's or it's going to be x's. So because we have one variable at this point, we should be able to solve for the value of that variable. Then once we have that, we're going to substitute that solution into either original equation. At this point, it doesn't matter which one you substitute that number into, and then you can solve for the value of the remaining variable. We should then write our answer as an ordered pair, x, comma, y. And this is assuming we get a value for each variable, right? We may not get a value for our variables, and that kind of brings me into our next slide. And as always, if you need more time to copy this down, feel free to pause the video or go back as necessary. So here are the three types of answers, the three types of solutions we could get when solving a system. You may or may not have already learned about this if you've covered how to solve systems by graphing. But if you're solving a system by substitution and your variable equals a number, variable equals a number. So for example, you solved for the x and you got a number, or you solved for the y and you got a number, you're going to have one solution. So the way that you're going to write your answer, your final answer, is going to be as an ordered pair, just like we said on the previous slide. Now when this happens, if you were to look at the graph of these two lines are intersecting at one distinct point. That's what's happening when we have one solution. Well, our variable doesn't always have to equal a number. Another thing that can happen is that our variables will completely cancel out. When we're trying to solve for a variable, our variable can completely cancel out, and we're left with one of two situations. We're either going to have no solution or infinite solutions. So what happens first in a no solution is that, again, your variables cancel out. Okay. And what you're left with is some sort of false equation. For example, 2 equals 5, right? So you tried to solve for the variable, but they ended up all canceling out, so you don't have any more variables and it's just numbers, and you're left with some sort of false statement like 2 equals 5. When this happens, your final answer is going to be no solution. You don't have a point of intersection, so you don't have an x and a y that you can put together. So think about what this means. Again, you may have learned how to solve systems by graphing at this point. So when this happens, when the lines don't intersect and you don't have a point of intersection anywhere, the lines are actually parallel. Okay, so let's go ahead and add that. The lines are parallel. They have the same slope. Another thing that can happen is, again, your variables might cancel, but you're left with some sort of true equation. In other words, you're left with an identity. We call these identities. For example, 2 equals 2, or 5 equals 5, or 0 equals 0. That's an identity. When this happens, when all the variables cancel out, when you're trying to solve for the variable and you're left with an identity, your final answer is infinite solutions, or infinitely many solutions. Whoops, I misspelled it. Infinite solutions. There we go. So think about what this might mean for our two equations. If you looked at the graph, and there's infinite solutions, that means there's infinitely many numbers of points of intersection. They're intersecting at an infinite number of points. They're intersecting everywhere. How can this happen? Well, if they're intersecting everywhere, if all of the points are points of intersection, the lines have to be sitting on top of each other. They're overlapping. This happens when the equations match. Okay? So we have overlapping lines, the equations match. They're exactly the same linear equation. So they end up, if you're looking at a graph, they end up being graphed in the same location. So these are the three types of answers that we can get. We'll just want to keep all of this in mind as we solve systems of equations by substitution. So let's go ahead and get started with solving some systems here. So we have two equations, two linear equations, and in the first equation, the y is by itself already. So I can actually skip that first step that said to isolate one of my variables. Well, this variable is already isolated. So I can move on to the next step that says take the expression that variable is equal to, which is this that I'm highlighting, and substitute that for the variable in the other equation. So if this algebraic expression is equal to y, then this y is also equal to this expression, and I can interchange them, okay? This top expression, or excuse me, this top equation tells me the two things are equal, so I can interchange it in the second equation also. Now when I do this, 8 times y in that second equation, that's what that means. It means multiplication. I want to show that that 8 is being multiplied to the entire expression. So the y gets completely replaced in parentheses with the expression that it's equal to. When you do this, notice that I no longer have any y's in that second equation. When you do this step, if you're doing it correctly, you should only have one variable. In this case, I have x's. It might not always be an x that you're solving for first, but it should only be one variable at this point. If you have two variables, an x and a y, you've done something wrong. Well, at this point, it's a multi-step equation that I know how to solve. I can distribute first. Oops, it's going to be a minus 48x plus, I believe that's 112. Let me double check. 8 times 14 is 112 equals negative 20. I'm going to combine my like terms. It's going to give me negative 44x plus 112 equals negative 20. And I'm going to solve the two-step. Subtract the constant. That's going to give me negative 132. Divide by the coefficient. And x equals positive 3. Okay, so I have my variable equals a number. That means I'm going to get one solution. I should get x equals a number, and then I can use this to help me solve for the y. So just like how I solved for the cat first on that logic puzzle, and then use that value to help me solve for the cheese, same idea here. I'm going to use the value from the x to help me solve for the y. So if I know I need to solve for my y, and I already have an equation where the y is by itself, that's going to be the easiest equation to use here. Remember, at this point, it doesn't matter which equation I substitute my solution into. The steps that we were looking at on that previous slide said at this stage, I can substitute this solution into either original equation, but the first one is definitely going to be the easiest. So instead of 6 times x, it's 6 times that solution of 3. Multiply first, combine the like terms, and there's the solution for y. Now that I have both of my variables, I can put them together as an ordered pair. X goes first, y goes second. There's my solution. Let's try another one. When you need to isolate a variable, look for coefficients of 1, -1, or multiples of that same number. So when I look at this equation, I don't have a variable already by itself, so I do actually have to do what step 1 says and solve one of them for one of my variables. So when you're solving for a variable, eventually you're going to have to divide by the coefficient that's in front of that variable. So always look for coefficients of 1 or -1 first. Those are the easiest variables to isolate. If you don't have a coefficient of 1 or -1, look for the equation, if there is one, where all of the other numbers are multiples of that coefficient. So for example, if I was looking at this top equation here, and I wanted to isolate this x, eventually I'm going to have to divide everything by -2. This will work out nicely if all of the other numbers are multiples of 2. So -8 is definitely a multiple of 2. 1, however, is not. This one wouldn't work out too bad, though. 1 divided by 2 would just be 1/2 or 0.5. But if I look at this bottom equation, this x has a coefficient of 1. That's going to be the easiest variable to isolate. So I'm going to use this second equation, x plus 4y equals 7, and I'm going to get the x by itself. To get the x by itself, I need to take this y term and move it to the other side. To move a variable term, we add or subtract. I have to subtract here. And there's the expression that's equal to x. So once I've got an algebraic expression equal to that variable, this tells me since these two things are equal, then I can replace that x with that expression. And remember, we're doing this in the other equation. So when you're isolating a variable, it's important to keep which equation is which in mind. When I isolated my variable, I was working from the second equation, the bottom one. So when I do my substitution step, I want to substitute into this top one. Really important that you're substituting into the other equation and not the same one. So instead of -2 times x, I have to open a set of parentheses, and in place of the x, I'm going to substitute the expression it's equal to. And when I do this, I only have y's in my equation, no more x's. I don't have both variables, I only have one. This allows me to solve, distribute, combine my y terms, and notice what's going to happen when I go to combine my y terms here. I'm left with a false equation. All of my variables canceled. So this is one of those special solutions that I talked about. When the variables cancel and you're left with a false statement, these lines are actually parallel. They're not going to intersect. There's no solution. That's my final answer. Whoops. Let's try another one. So again, I don't have a variable by itself, so I'm looking to see if I have a coefficient of 1 or -1. Unfortunately, I don't. So at this point, I have to make a choice of which coefficient do I think is going to be the easiest to divide everything by. Well, this one actually doesn't work out too bad. If I try to isolate one of the x's here, regardless of which one, I'm either going to have to divide everything by +2 or by -2. Everything else is an integer. When you divide an integer by 2, one of two things is going to happen. You're either going to get a nice integer or you're going to get a terminating decimal. Same thing if I was to isolate the y. I would eventually have to divide everything by a 5 or -5. So when you divide an integer by 5, one of two things is going to happen. You're either going to get an integer or a terminating decimal. So it really doesn't matter which variable I isolate here and in which equation. So I'm just going to isolate the x in the second equation, so that way eventually I just divide everything by a +2. But you always want to think about that. Think about what types of numbers you would be left with if you divided everything in that equation by that coefficient. Numbers to avoid are numbers that will give you non-terminating decimals, okay, or really funky fractions. If you're getting a decimal that keeps on going, that's probably not the best variable to isolate. So I'm going to take this bottom equation. To get the x by itself, I have to first move the y term over. I do that by subtracting. And the next thing I have to do is divide everything by that coefficient. If I divide 12 by 2, that gives me a nice integer of 6. And -5 divided by 2 works out nicely as a terminating decimal. So now that I have the x by itself, I can take the expression that x is equal to and replace the x in the other equation with that expression. So again, I was working with the bottom equation, so I'm substituting into the top. The x gets substituted with this algebraic expression that has a y. So at this point, I should only have y's. I shouldn't have any x's as well. And I can solve for this value of y. I'm going to distribute first. -2 times 6 gives me -12. -2 times -2.5 gives me +5. I'm going to combine my like terms, and they're going to cancel. So we're going to get a special solution here. And look at what I have. I have -12 equals -12. That's true. That's always true. So I have an identity when that's the case, we have infinitely many solutions. What's happening here is that the lines are actually overlapping. If we were to look at the graph, they're intersecting at every point. If I was to get both of these equations in slope-intercept form, they would be the exact same equation. Or another way to think about it, look at them in standard form. They're the same exact equations, the only difference is their signs are opposite. But if I multiplied this top equation by -1 so that the a value would be positive, they would exactly match. Okay, so they're the same equations, so if we were to graph them, they'd intersect everywhere. We have infinite solutions. Okay, so I briefly showed the solutions there. I didn't mean to, but go ahead and take a look at these equations that have not yet been worked out and give them a go on your own. And when you unpause the video, I'll go back to that slide that had the answers. Okay, so hopefully you've given that a go. Here's what I'm getting when I solve the systems. For the first one, the y variable was already by itself, so I took that expression, substituted it for the y in the second equation, attempted to solve, got an identity, so we have infinite solutions. For number 5, we did not have a variable by itself, so the easiest one to isolate was the x, in my opinion. The y down here would have worked out okay as well. It just has a negative in front of it. But coefficients of 1 and -1 are the easiest variables to isolate. To isolate the x in that top equation, add the 2y away from it, then take this algebraic expression for the x, substitute that for the x in the bottom equation. When I did this, and I solved, I got y equals 2. I can then take this solution, and I know I'm going to get one answer here, one solution, because my variable equals a number, and I can substitute the solution into either original equation. It doesn't matter if I substitute the 2 in this equation or this one. We should be able to solve for the x regardless. I simply used the top because I thought that one looked the simplest, but it should work on the bottom regardless. And I solved and got an x value of -1. The last thing I need to do when I'm getting one solution like this is to put those values together as an ordered pair. And then number 6, this one was kind of a challenge. You don't have any coefficients of 1 or -1. You also don't have like really nice numbers where the other values are multiples of one of those coefficients. So my strategy here was to start with a coefficient and divide all the other numbers in that equation by that coefficient to see whether or not I'd get a repeating decimal or a terminating decimal. When I did 3 divided by 8, I got a terminating decimal. Same thing when I did 7 divided by 8. So I said, you know what, I'm going to get decimals probably no matter what I do, so I'm just going to go ahead and isolate this x because now I know that I'm going to get terminating decimals for them regardless. So isolating the x in that top equation, the first thing we should do here is add the 3y. Then again, you're going to eventually divide everything by that coefficient, and here were the terminating decimals I got. So I'm going to take that algebraic expression equal to x, substitute it into the x in the other equation, which would be the bottom one. When I attempted to solve for my variable y, I got a false statement. I got a false equation, so this is no solution. So these types of systems here for number 6, those are the particularly challenging ones. The reason, again, I went for the 8 and isolated the x is because if I tried to isolate the y here, think about it, you're eventually going to have to divide everything by 3. Well, if I did that, if I divided 8 by 3 or 7 by 3, that's going to give me a repeating decimal. You never want to go for numbers like that because you're going to be forced to either round or leave it in fraction form, which you can do. But I always prefer making them terminating decimals when possible. I think it's just easier and quicker to work with. But this comes with practice, being able to identify which variable is going to be easiest to isolate. So hopefully this video helped. And as is typical, if you have any questions, reach out to me or one of your teachers, and I will see you guys.